Welcome back. In previous lecture, we started with our discussion of the topic called transistors. Transistors is the name of a big, broad class of devices which include BJTs as well as UJTs. On that day, we primarily discussed PJTs, BJTs that stands for bipolar junction transistors, and we saw how important their output characteristics are. The constant output current not varying with respect to the output voltage makes it suitable for making it an amplifier. But before we understand how an amplifier works, we also need to discuss other types of transistors as well and their comparisons. So BJT, which stands for bipolar junction transistor, has a different kind of conduction mechanism through it. For example, this is a NPN transistor and electrons are majority carriers in emitter region. They get diffused across, before they reach the collector region, they have to cross two junctions, and across the junction they basically diffuse through it. This is different from a normal drift-based kind of conduction that takes place in a normal, say, conducting wire, say copper wire. If you put one end of the copper wire as positive and the other end you apply some negative potential, what happens? The electron get drifted across this conducting wire towards the positive terminal. Obviously, they during their motion, during their journey from negative to positive, they collide among themselves and with positive kernels, and they cause some kind of Brownian motion in those electrons. But the electron starting its journey ultimately reaches out at the positive terminal. It gets drifted along with its Brownian motion. This is not the case over here. The electron which started its journey may get neutralized by some hole, and at the same time some other covalent bond breaks and new electron is produced. That electron starts the journey further. And across the junction, they diffuse across the junction, which makes the process a bit slow. So BJTs are relatively slower devices because they have got diffusion based conduction, not drift based conduction. So let's see a few properties, rather a few limitations, some bad points about BJTs. Although they are extremely good device, they're very good. That's a very good device. The output characteristics are marvelous, but at the same time, the diffusion based conduction makes them a bit slower devices. Simultaneously, there is another point that it's a current controlled device. The output current somehow is controlled by the input current and not by the input voltage. That means whenever we want to use it as an amplifier, we'll have to convert the voltage signal into a current signal. If the input signal is voltage signal, you'll have to convert it into a current signal before you can amplify it using a BJT. What if I need a voltage based amplifier? That means voltage controlled device would be needed for that. That means the input signal in form of voltage signal can be amplified directly. We'll see how can that be done in other devices. And simultaneously, one more point need to be discussed, that they have got higher noise level. Now what is noise? Noise means unwanted electrical signal. Whenever an electron hole combination is taking place, some energy is being released. That energy causes unwanted electrical signals across at the output junction. Now what happens if, let's say, a song being sung by a singer is being amplified and some unwanted electrical signals are coming along with that. So you will have the song getting amplified. Along with that, at the output you will find unnecessarily unwanted electrical signals, which if they go to the speaker will create blum blum bleepy kind of sounds, which is obviously not required. We need filter circuits to filter them out. The problem the BJT has, that it has got higher noise levels. Now there is one more problem with that, the BJTs. Their input, that is the emitter base junction, is always forward biased, and collector base junction is always reverse bias. So output impedance is quite high and input impedance is quite low. So the ratio of output impedance to input impedance turns out to be extremely high. Actually, that's the point from where the name transistor has been derived. It's basically transient resistor. At the input you have got low resistance, at the output you have got high resistance. If you move across the transistor, there is a transition from low resistance to high resistance region. That's why the term transient resistor or transit resistor has been termed as transistor. So they have got impedance ratio which is very, very high. Now why that's a problem? You know, whenever you want to transmit a signal, let's see, I've got an oscillator and let's forget it. Let's take a simple example of a simple rope. You are holding on to a rope and you are swirling it to create a wave. Now, the second end of the rope, if it is tied to a wall, what will happen? It will just bounce off the wall. If the impedance offered by the rope for the transmission of this wave through it is quite low in comparison to the impedance offered by the wall for the transmission of the same wave through it. This impedance is high, this impedance is low. So what happens? The signal doesn't get transmitted properly to the wall, rather it will bounce back. So whenever you wish to transmit a signal from one device to another device, the output impedance of this device and input impedance of the second device, the receiving device, should be comparable. If they are not comparable, what will happen? The signal transmission will not be efficient. So we need to match these impedances. So this is called impedance matching. Actually, if this has got the output impedance as Z1, this has got input impedance as Z2, the transmission medium should have impedance Z3, which is equal to Z1, Z2 square root of that. Now, if this is not met, the signal transmission becomes a problem. Now, when this has got a high impedance ratio, that means at the output the impedance is high. As you transmit the signal from transistor, the other device which is receiving it, which may be another amplifier or which may be an output device, a speaker or a picture tube or any other device, that device should also have high input impedance. Only then the signal from this BJT can be transmitted to that, at least in common base configuration. Now this is a problem in itself. What if we can deal with this? That would be, it's not a problem which cannot be dealt with, but this makes the things a bit difficult. So we can think of another device which will do things which are quite same as a BJT does, but will have problems either not present, or even if they are present, these problems will be of lower magnitude if we use those devices. And the category of transistors which is the answer to these problems is what we call as UJTs. This is unipolar junction transistors. A word of caution here. I am dealing with here a family of devices called UJTs, that is unipolar junction transistors. Unipolar junction transistors, which are junction field effect transistors or metal oxide semiconductor field effect transistors put together called as one category. But there is one device also called UJT. That stands for unique junction transistor. This is unipolar junction transistors, and this is what we call a unique junction transistor. It's the name of a device as well. Don't confuse the name of that device as unique junction transistor with the family of transistors called unipolar junction transistors. The unipolar junction transistors, the family of this family of transistors can be subdivided into two, as I said earlier, the junction field effect transistors and the metal oxide semiconductor field effect transistors. In this lecture, I will discuss this FET and will show you how it produces the same output characteristics as a BJT does. That means wherever you can use a BJT, the FET can also be used. So if you can make an amplifier using a BJT, you can also make an amplifier using FET because its output characteristics are identical. So let's proceed with this. What is an FET? A FET has got one single crystal bar of one type of semiconductor, say n-type semiconductor. Let's say this is n-type semiconductor. We have doped one region on this side and one region on this side with the other type of. We have done doping in such a way that this region and this region becomes the other type of semiconductor. Let's say p-type semiconductor. This is p and this is also p. So two junctions will be formed. One over here. This is n region. So this is a PN junction over here and this is a PN junction over here. This and this are internally connected and commonly connected to a terminal called gate. There are two more terminals to the this bar of semiconductor. The one side is that from where the charge carriers will enter the semiconductor bar. That is called source. And the other terminal is that from where these charge carriers will make an exit. That's basically draining out. This end, from this end, the charge carriers are draining out. So this is called drain. As in BJT, I gave you two golden rules that emitter base junction should always be forward biased and collector base junction should always be reverse biased. In this case, the golden rule is that gate should always be reverse biased. Let's see how it works. Now this is a n-channel FET. This gate has been connected. This is P, so to reverse bias it, I connect it to negative and connect. Source is common in this case. So this is a battery. I call that VGG battery. The voltage across gate to source is VGS. And then I've got the source to drain. How a battery should be connected over here? As I told you, the charge carriers must enter from source and they must drain out from the drain. So this is an n-channel FET. So charge carriers are electrons. So electrons should enter from this side. So this side should be connected to negative. This is VSS battery or VDD battery, and this voltage across this is, let's say, VDS voltage. Now this is the current which is flowing from here. You can see if electrons are going in this way, the conventional current I can measure as ID is traveling in this direction. So drain current is in this direction, but remember that electrons are flowing in this direction. The conventional drain current is in this direction. Now look at the situation, how this is going to work. Since this is a gate and gate has been reverse biased, it creates a depletion region around these terminals. And in addition to that, as the current flows, this is, you can see, this is a single bar of semiconductor, and as electrons will flow across this, there is no junction which they will have to cross over, as it was the case when the charge carriers were crossing from emitter to collector through two junctions. But in this case, there is no junction in between. The junctions are on the sides. The electrons will just drift across to the drain. So that's why I told you that this has got drift based conduction, and all those problems which arose in case of BJT being a diffusion based conduction device, those problems would not be present over here because it's a drift based conduction in this device. Now electrons are going to drift to the source, And as the electrons are traveling, this bar of semiconductor will act like a resistor. And we know when current flows across this end becomes, this end acquires higher potential and this end is at lower potential. That's why current is flowing from higher to lower potential now, obviously. So this end is a little higher. The end region is getting a little higher value of voltage, and the lower region is getting a little lower value. So you can see this N region and this is P region. P is less positive than N. So this also creates a reverse biasing. The flow of the current causes a potential drop across the bar of this semiconductor, and that bar of semiconductor causes what you can say another reverse bias. That will create a reverse bias, and another depletion region will develop across this. You can see I have made this depletion region. I have made this second depletion region in the shape of a wedge. This is because the higher end is at higher positive potential than the lower end. So at the upper end there is more reverse biasing than at the lower end. Now what happens? I can name these depletion regions. Let's say there was one depletion region which was created because of this reverse biasing voltage VGS, and I call that number 1, and there is another depletion region which is created by the flow of the current, and that's what I am calling it as region number 2. What will happen? Let's say I keep VGS constant, and I increase this VDS voltage slowly. As I am going to increase the VDS voltage, this second depletion region will go on increasing, and at one voltage a stage will come at one particular voltage when these two depletion will just touch each other. As soon as they touch each other, what will happen? This second depletion region will vanish. Will it not? Because the second depletion region was there because of the flow of the current creating a potential drop across this bar of semiconductor. If the two depletion regions touch each other, there will be no current. And if there is no current, there is no potential drop across this bar of semiconductor. And since that potential drop was causing the second layer of depletion region to be present, the second layer will vanish. And as soon as the second layer vanishes, the channel again opens up and suddenly large current will again flow, and suddenly the second layer of depletion region will again be present. Will this happen? Actually no. Actually they will strike a compromise. What will happen? As soon as the depletion region goes close to each other, as they go close to each other, what is happening? The width of the channel is decreasing. The width of the channel is decreasing. As the width of the channel is decreasing, it will increase the resistance of that second region, this channel. That will increase the resistance of the channel, because the resistance is given as rho L over A. A is area of cross section. As the area of cross section of the second region is decreasing, what will happen? Its resistance will increase. That increased resistance will limit the current, and current will never rise to a point where the depletion regions can touch each other. So by increasing VDS, you will not be able to increase the second region of depletion region so much so that they can touch each other. They will not be able to touch each other. What will happen? What will happen? A small channel will remain there. I repeat, if you try to increase this voltage, the potential drop will tend to increase. The depletion regions will tend to come close. As they tend to come close, the width of the channel will decrease. That will increase the resistance of the channel, and subsequently what will happen? That will decrease the current. So if you are trying to increase the current by increasing the VDS voltage, I repeat, if you are trying to increase the current by increasing VDS voltage, that increase in current would be compromised by increase in resistance. So current will never increase to that limit where the channel can be closed. Actually, a small width would always remain. That means at that point the current will become constant. Even if you decrease the voltage, VDS, what will happen? The channel will open up. So by decreasing voltage, you were trying to decrease the current, but the opening up of the channel will increase it. And if you increase the VDS voltage to increase the current, the channel width will decrease and again will limit the current. So current will remain constant independent of this voltage. So what would be the output characteristics? What is drain current versus VDS voltage? I need not to tell you that the curves are constant. These curves, I hope, reminds you of output characteristics of a BJT. They are exactly identical. So if in this region a BJT was used as an amplifier, could be used as an amplifier, and FET can also be used as an amplifier in this region. So an FET also works as an amplifier, which we'll see how in the later lectures. But the primary thing which I wanted to bring home in this lecture was that how the constant current output characteristics are obtained for an FET. And if you keep this thing constant and increase this VGG or VGS, obviously these are called transfer characteristics. That's very easy to understand how that will work. I'll show it in the negative direction because this has been reversed. This is reverse wise. So graph between drain current and VGS would be something like this. If you keep on increasing this voltage, the region number 1 will increase. The depletion region number 1 will increase, and ultimately that can touch each other, and finally that can pinch off this FET. By the way, pinch of voltage is that where this current becomes constant. That's a VGS voltage. The VGS voltage, the value of VGS voltage at which this constant current characteristics are obtained for an FET is termed as pinch of voltage for it. And when VGS is 0, the maximum current, this is IDSS, drain to source current. These are called transfer characteristics or input characteristics. In the very similar way, we can also obtain the characteristics of MOSFET as well. But that we'll do in some later lecture. In the coming lecture, I'll discuss MOSFET, and then we'll come back to amplifiers using BJTs. Thank you.